Welcome back, everyone. This is Chapter 2, Section 2, our second video, 222, and this one's titled, Why Not Differentiable? And the claim is there are some different ways that a function can fail to be differentiable, and we would like to be able to identify those, not only from the equation, but also graphically. So we saw back in example 1.7, remember this is the one with the absolute value, you can scroll up to that if you need a little bit of a refresher. But there are ways in which a function can fail to be differentiable, right? The derivative is defined by a limit, and limits don't always exist. So in this video, we're going to explore a variety of different ways that this can happen. And the first way is going to be the exact kind of way that this example 1.7 failed, and it's because it had these jagged edges, or kind of more formally, this is sometimes referred to as a cusp. So because the derivative is a two-sided limit, as h goes to 0, if the left and the right-hand limits do not agree, the function will not be differentiable. So again, we saw this in example 1.7. Graphically, these look like jagged edges. So another example of this is here. We have this function. And we have kind of a slick type of question here. It says, just based on the graph, right? We don't have the equation at all. Determine any points where f of x is not differentiable, and explain why it fails to be differentiable there. So I look here, and of course we're going to be using this first case. We see that it's nice and smooth. There's no jagged edges anywhere in here. And then all of a sudden at 3, right? At 3 kind of you have this abrupt change. So at x equals 3, f of x is not differentiable. And let's think about this kind of as a term of limits, right? So thinking about the slope. As we approach 3 from the left, the slope seems to be, kind of maybe approaching even 0, right? It's positive, but then it's getting smaller and smaller. It's kind of leveling out here. The slope seems to be getting close to 0. But then after 3, if we were to consider a right-hand limit, after 3, the slope's kind of constant, maybe like -1 or something like this. So let's go ahead and say, as x approaches 3 from the left, the slope seems to approach 0. However, as x approaches 3 from the right, the slope is constant, like -1. And so remember, in order for a two-sided limit to exist, which the derivative is, we need the left-hand limit and the right-hand limit to agree. So because 0 and -1 are not the same number, this limit will not exist. So again, since the left and the right-hand limit do not agree, the limit will not exist. Again, this is the two-sided limit will not exist. All right, and so again, we see this anytime we have one of these jagged edges, or more formally, cusps. This is not the only way in which a function can fail to be differentiable, though. Another way it can fail to be differentiable is that if it is not continuous. So this is our second case. So in this case, the left-hand limit or the right-hand limit, again as h goes to 0, will not be a real finite number. Graphically and algebraically, we know how to spot discontinuities. We've become very good at this back in chapter 1, right? We were very interested in discontinuities. When is a function continuous? This also leads to another important theorem. So, right, if f is differentiable at a value c, then it is continuous at a value c, right? Because if it wasn't continuous, then there's no way it could be differentiable. So the only way it can be differentiable is if it is continuous. So that's another kind of almost rephrasing of this second case. And now let me go ahead and kind of show you graphically again kind of what these words are trying to tell us. So I went ahead and made a little Desmos graph for us here. And we can see that this function is not continuous at x equals 1. And so the claim is that this is not differentiable. But in order to really verify this, we need to go back to the definition of the derivative. So I went ahead and I graphed out some secant lines, right? And so as our h value changes, again, h should be going to 0, but it can head to 0 from the left and from the right. So if h goes to 0 from the left, we can see that we're getting closer and closer to the value 1. And as you get closer and closer, let's even do very, very small, negative 0.01 or something like this, you can see that this slope, it's negative. It seems to make sense. It's negative, though. Now, on the other side, let's look as we approach 0 from the right. So as we approach 0 from the right, look at what's happening. So we're going to start going more and more positive. So as we do 0.1, sorry, this line's it's getting more and more negative, right? The slope of this purple line, which should be the derivative, is getting more and more negative. As we do something like 0.01, you can see that this slope seems to be, the line seems to be almost straight up and down. And what is the slope of a straight up and down line, a nice vertical line? Well, the claim is that it's undefined. And even as you get even closer to 0 from the right in this case, right, it really looks like a vertical line, like it's straight up and down. So again, the idea here is that in this case, as we approach from the right, limit as h goes to 0 from the right, this will not be a real finite number. In this case, the slope seems to be heading towards like negative infinity, because again, what is the slope of a straight up and down line or a vertical line? Well, it's not a real number.
All right, let's go ahead and consider this following example where we have a nice piecewise defined function.
And the claim is that it is not differentiable at x equals 3. So of course we're going to be using this stuff up here, but let me note really quick that if you were to just kind of blindly think about maybe the derivative of this first function and the derivative of the second function, remembering that the derivative is slope, well, notice the slope of this function is 1, the slope of this function is 1, and so you would say, well, maybe the slope is 1 and it is differentiable. You know, if I worded this question slightly different and asked, is this differentiable at x equals 3? You might say yes. But the claim is that it is not, because we do have to think about, is it continuous at x equals 3? So this really is now a question that belongs almost in chapter 1, right, when we were thinking about continuity. And remember, so for a function to be continuous, we need that the limit, in this case as x goes to 3, since we're interested in at 3, for our function should be equal to f of 3. And in order for this to even make sense, remember the two-sided limit needs to exist. And that's what I'm kind of worried about, because as you approach from the left, we have one thing happening. As you approach from the right, you have a different thing happening. And so the question, do they approach the same value, right? Otherwise, if the two-sided limit will not exist. So let's go ahead and consider, right, the limit as x approaches 3 from the left. So remember, as I'm approaching 3 from the left, I'm over here. I'm in values that are smaller than 3. So values smaller than 3, that's going to be this first line, right? If x is less than 3, smaller than 3, the function's determined by x plus 1. So the limit as x approaches 3 from the left of our function is going to be the same thing as, well, x plus 1 in this case. Now that I've simplified it down, we can see there's no problem in just using this direct substitution property. So I'm going to plug in a 3 everywhere I have an x, and that's going to give me a value of 4. On the other hand, if I'm approaching from the right, 3 from the right, I'm over here. These are values that are bigger than 3, things like 4 or 5, 3.1, 3.01, since we're getting closer and closer to 3. So that's going to be when x is larger than 3, right? Approaching from the right. So now my function is going to be determined by x plus 2, this piece. Again, there's no problem just using the direct substitution property. So plugging in a 3 everywhere I have an x, I get 5. So in this case, at the value 3, actually the left-hand limit and the right-hand limit don't agree. So the two-sided limit doesn't exist, and therefore the function is not continuous. So f of x is not continuous at x equals 3. therefore, it is not differentiable, which I'll denote DIFF, at x equals 3. So remember, whenever a function is not continuous, it is not differentiable. All right, the third and final case that we talk about in this class is that sometimes you have a vertical tangent, right? So in this final case, the tangent line could be vertical. So again, the slope will not be a real finite number. So let's consider this function right here, the cube root of x. This is kind of a classic one. Sketch the tangent line at x equals 0 to see that the derivative at 0 there does not exist. So the tangent line at 0 here, well, if I want to just barely skim the function, notice that it's pretty much straight up and down at that point. So my tangent line is going to be pretty much straight up and down. It is vertical. And so what is the slope of this vertical line, this vertical tangent line? Well, it doesn't exist, right? For vertical lines, they don't have slope. It's undefined, as we probably recall from our good old algebra days. So let's go ahead and just write something down. So since the tangent line is vertical, its slope is undefined. So this is a case where we have a vertical tangent. Case 3, just like, case 3 says. All right, so those are the three big cases. These are the things to watch out for, why a function may not be differentiable. All right, that's the end of this video. I got one more for you when we're going to take more of a graphical viewpoint. So I'm going to give you a graph of a function, and I would like you to graph its derivative. All right, I'll see you then.